Vahagn.
Yes. Yes. Abgaryan from Dubna, from OEA. Where is here? This microphone for you. Okay. And he's in your pocket.
Я поставлю, не беспокойтесь. Угу. Угу. Так. Да. Давайте лучше вот так.
Ага, так наверняка.
Угу. Все?
Да, я думаю, что...
Вот так. Okay, may I start?
Yes.
Yeah,
Vahagn
okay.
Abgaryan, the first speaker of our session.
Yeah. First of all, I would like to thank the organizing committee yet again for this opportunity to deliver a talk in your beautiful city. This is the first part of the thanks, and the second part is for yesterday's second session devoted to Vladimir Petrovich's memory. It was very touching. So thank you. Okay, moving forward, my presentation is entitled Classical Fisher Information Metric from Wigner Quasi-Distributions. And since the first talk by Martin, my talk, and the next talk are interlinked together, I would like to give a little bit of context, first of all. Second, to tell you about the problem, generally the problem, a little bit of application of computer algebra, then to speak about the open questions. So I will try to explain the context like a Russian doll. In any parametric statistical theory, there comes time when you want to estimate your parameters from information about measurements on some random variables. This gives rise to information theory, be it classical or quantum, doesn't matter. Then, since our estimations are to a certain degree of accuracy, we want to measure from the true probability distribution or true parameters the value that we got. We want to introduce certain distances. This gives rise in turn to information geometry. Now, and the main object in this information geometry, one might consider the Fisher information matrix, which plays a role of Riemannian metric on the manifold of probability distribution functions, and etc. On the other hand, in quantum mechanics, this is the case. We have results of some measurements which are random. After some point, we want to recover the state, and one might consider quantum mechanics as a parametric model of the nature on certain scales where you have these results of random measurements, random results of measurements, and you want to recover the state. The state itself is the parameter in that case. However, a trivial approach, a straightforward approach, is not fruitful in this case because there are some very principal obstacles on the way of interpreting quantum mechanics as a true statistical theory. What we want to do in this work here is to yet again try to do the impossible. We want to ask whether there is a submanifold, at least, of some states which can be mapped on probability density functions to introduce classical Fisher information on this manifold, to interpret it as a distance in the state space, then to see whether it's possible to extend this definition to the whole state space. So this is the problem. Okay, you can see here the metric tensor defined as the Fisher information matrix. Let's move forward. So how do we attempt to solve this problem? It is well known probably to most of you who dealt with quantum mechanics that there is a quasi-probability distribution function called Wigner function, which may be interpreted as a probability density function. However, it lacks certain properties. And the way to construct these functions is by Stratanovich-Weyl postulates. And according to these postulates, to each operator acting on the Hilbert space of n-level, let's say, quantum systems, there exists a mapping, a linear mapping, to the space of functions which behave like probability density functions. And the set of postulates is the following. First, the linearity of mapping. Then the kernel by which the mapping is performed must be Hermitian. Then it must be the integration over the whole phase space over this kernel must be unit. Then the reconstruction, which says that if we constructed a probability density function for a given state, by the same kernel we can perform the quantization. And basically, we have the reconstruction postulate, which says with the same kernel, you can recover from the given Wigner function the state itself. The next property is called covariance, which means that to unitary transformation of a state sort of corresponds backwards transformation of the state space itself. You can see the definition by the formula here. So basically, Wigner function is constructed as a dual pairing of certain elements. One is an element of this Pn, which is the state space, basically the space of complex matrices n by n, which are Hermitian, positively semi-definite, and fulfill the triviality condition. It might be shown that the previous postulates boil down basically to these two algebraic equations on the kernel, leaving n-2 parametric freedom for fixing the kernel itself. And the dimensionality of the phase space, its structure is defined by the isotropy groups of the state and the isotropy group of the kernel. Basically, the second definition gives you the dual to the state space, which is the space of Stratanovich-Weyl kernels. Again, they have to be Hermitian, fulfill the triviality condition, and also there is a restriction on the trace of square of this operator. Now, if you are given a state described by this density matrix, rho, then you may construct a Wigner function which is representable by this simple, deceivingly I would say, simple formula, where zeta fixes the state. Zeta is the block vector corresponding to the state matrix, or in other words, it parameterizes the whole state space. And nu here is the moduli parameter which fixes the kernel, because you have n entries on the diagonal of your kernel, two equations restricting them, and nu fixes basically the solution to the kernel, let's say. Here n contains the information about the phase space parameterization, and also the moduli parameter of Wigner function. Now, this function is good and everything. It behaves like a probability density function. Any convolution with other symbols corresponding to the system give you the expectation values of these quantities. However, it lacks a very crucial property for probabilities. Basically, it may be negative. This is the reflection of the principal obstacles that I was talking about. However, there are two regimes of classicality in this scenario. First, if you're, as you can see from the scalar product structure of this function, if C or the block vector is shorter than certain length, then your function is always positive, independently from the choice of your kernel and etc. These states we call absolutely classical states because it does not depend on the choice of our choice of kernel. Second, an optimal bound for Wigner function says that if you have Startanovich-Weil kernel with pi eigenvalues and r eigenvalues for your density matrix, this quantity is the infimum of Wigner function, and this quantity is the supremum. But this depends, of course, on the choice of kernel. So we call these states conditionally classical states. We will restrict now ourselves with only the case when the block vector is shorter than psi asterisk. But it doesn't matter. Everything that I talk about might be done for the conditional case too. Basically, we define the Pn plus state space as the collection of elements from the state space which fulfill this requirement. Now, for the elements of this state space, or of this Pn plus, we may introduce without any problem the Fisher classical information matrix. Now the problem boils down to trying to calculate this information matrix and interpret it as a metric on this classical, on this manifold of classical states. How to do it? It is more or less easy to show that this matrix may be shown, may be represented in this form, which is very good, but however, it is divergent. But let's keep this problem for a minute. Now we perform integration by the phase space of this expression, and to do that we apply the Harish-Chandra, sometimes they say Harish-Chandra-Isaacson-Zuber theorem, and basically what it says is the following, that if you integrate such kind of structure over the whole space of unitary matrices, then the answer is the following, where deltas, delta A and delta B are corresponding discriminants of characteristic polynomials corresponding to A and B. Now, there is a way to regularize the divergency of the integral, and if you perform that, you will finally arrive to this kind of short expression, yet again, deceivingly simple, which says that you have here chi omega, which is a pairing of eigenvalues of the Startanovich-Weil kernel and state itself, the density matrix. Omega is an element of alternating group, while omega prime denotes all the possible odd transpositions, permutations, I'm sorry. And P omega is just the matrix performing the omega alternation. Now, let's move forward. As you can see, this formula, yet again, is very simple, but if you start to evaluate it for systems larger than 2, let's say systems of three-level quantum systems, it is impossible to even calculate the directly calculate the volume element dictated by this metric. And here comes the computer algebra part. So I tried to feed this into Mathematica, and in 3 days, I was just curious whether it will be able to do so. It didn't calculate the determinant of this matrix in 3 days on my personal computer. So there must be a way to deal with this kind of problems, with this kind of metric tensor. And here, as an example, I give the prescription of how to deal with it on the example of three-level system. So a three-level system is described by this kind of psi, again, block vectors, which must fulfill these restrictions. So the rho is positively semi-definite. Basically, R must be less than 1, and D, I, J, K are the structure constants of SU3 algebra, while lambdas are just usual Gelman matrices. So let's observe some observations. Even though the block vector parametrization allowed us to come to the final answer in this form, because it was crucial that Wigner function is linear with respect to the block vector parametrization of the state space. However, it is impossible to calculate even the determinant. On the other hand, let's say you want to calculate the volume element. How to do it? Intuition says that in the SVD parametrization of the state, at least the volume form must factorize into tangent block, which contains the information about the unitary coordinates of the state, and the radial block, which reflects the SUN invariance. Basically, one might even expect that the whole metric tensor in these coordinates would be block diagonal, containing tangent and normal radial parts. However, it's not true, and it has to do with the vector parametrization of SU3, even though the parameter space of SU3 is kind of topologically equivalent to S3 times S5, it is impossible to separate these vectors and to say that we are going to parameterize the whole group by one 3-dimensional vector and separately a 5-dimensional vector. These vectors are intercoupled with each other, but the volume form is going to be factorized. So what we do is the following. First, we say let's consider the characteristic polynomial corresponding to the metric tensor. It is representable in this form. Then we say, okay, let's give the parameterization of the density matrix by the solutions to this characteristic polynomial and also some unitary matrices. Okay, this is the trigonometric parameterization of the solutions to this equation. On the other hand, we need the next ingredient to construct the Wigner function. We need the Stratonovich-Weyl kernel, which is parameterized as follows. If you do a little bit of algebraic manipulations, in the end, you may represent your metric tensor in the following form, where already you get these chi i's and chi bar I, which have the zeta parameter, which parameterizes the Stratonovich-Weyl kernel here, intercoupled with theta, which parameterized, which is a SU3 invariant of the state. Okay, after that, we move forward. Even in this form, Mathematica can't compute the determinant of this matrix. What to do next? Basically, what we say is the following. Okay, let's pass to the coordinates corresponding to the SUN invariance, because the function that we differentiate to get the metric tensor is dependent only on the eigenvalues. I introduced here some notations. They are not very important in this context yet now. Now we want to calculate the determinant of this matrix. We represent it by the traces of some orders of the matrix itself, and after that, some pattern matching programming, we get a final result which is very simple, even though Mathematica was not able to directly compute this thing. I already finalized this program, and I hope that soon enough it will be available together with the publication of this paper, so people can do that for other dimensions too. Now, I want to conclude and to say the following again. First, we want to map some set of states to classical density functions space. Then we want to introduce classical Fisher information on this state space. Next, we provided a way to compute everything basically for this metric. Second and third, we ask, is it possible to extend this definition to the whole state space. The answer is yet unknown. However, the certain Covariance structure of the metric tensor leaves some hope that it will be possible to extend the definition to the whole state space. And the third question, which is not less important, concerns with the monotonicity of the metric that we have computed. And there is a question whether there is a parameterization of the Stotanovich-Weyl kernel which would bring us to the monotonicity condition fulfillment. However, these questions are yet open. This is an ongoing process. Now I want to thank you for your attention. Hopefully I did not bore you to death. Thank you.
Thank you very much. Have you questions? Oh, I have a question.
Yeah.
Let me know, what is your next step in your research in this direction?
Basically, what we want is to extend this definition, which we gave for classical state manifold, to the whole state space to see whether it's possible to do. And the second, as I said, to see whether there exist such restrictions on the Stotanovich-Weyl kernel which will bring up the monotonicity of the metric that we got. Because in general, it's not monotone. And monotonicity is very crucial for quantum information theory.
Would it be some stage when you can take some material and make some models and to compute some results? And
basically, we provided here the metric for the three-level system. So for three-level systems, you have a notion of distance by these formulas by which you can estimate, you can say how far off is your estimation from the true value. This is basically the idea. It is, it's not applied physics, it's just quantum information theory. That's it, basically. Yep.
More questions? We have some more time for discussion in this direction. I have to mention that Vahagn from the same department, from the same laboratory as Volodya, and he is this young mathematician that was. Volodya was one of the pioneers in the quantum computation in Russia. One of the pioneers, and very nice that today we can see the young mathematician in the same region of science. And so next speaker will be two from the same department and in the same direction. Let's thanks to the speaker once more.
Thank you.